welcome back. So today we'll be talking about Truncus and how we can graph it from seeing a rule. So Truncus, just to begin with, we're going to follow this general form over here. So it's got generally you're going to see the graph of 1 over x squared, but we're going to change this a little bit. So sometimes you can have, instead of 1 at the top, it's going to be a. This a value represents the dilation away from the x-axis. So we're not looking at the value of a really, we're actually looking at the size of it, the magnitude of a. So it doesn't matter if it's positive or negative. The h over here, if you grab the h next to the x, it has to be inside the square, then the h value means it's going to be translating horizontally. So if it's positive, then that means we're going to go to the right. Negative, going to the left. The k value at the end over here, just like many polynomials, the constant that you're adding to the end represents the vertical translation. So it's going to go up or down. Up if it's positive, down if it's a negative k value. And of course, we only talked about the magnitude of a here. Similar to hyperbolas, if a truncus has a negative a value, then this means that you're going to reflect from the x-axis. So you're going to flip it upside down. Okay, so quick diagram here for a quick summary of how the truncus works. And of course, if the a value is negative, you just flip it upside down. So make sure you're flipping it with the x-axis. Copy these questions down. And if you want to have a shot at them, pause the video, have a shot first. Otherwise, I'll go through the examples now. Okay, so for this one over here, I like to go through all of the transformations first. And before we even do that, we can see if it's in the right form. Seems like it is. We can clearly see what the a, h, and k values are. So over here, the a value is right at the top. This a value represents the dilation away from the x-axis. So this is equal to 2. We don't have a h value here. This is the same as saying x minus 0 all squared. So this means that our translation away from, our translation in the horizontal direction is going to be 0. So you don't even need to write this down. And over here, we have a translation in the vertical direction, upwards by 3 units. So translation in the y direction, positive 3. Okay, the reason why we always write down translation is so we know where the asymptotes are. So when I draw this graph out, okay, so the horizontal translation used to be at y is equal to 0 along the x-axis. We're going to move that up by 3 units now. So around here somewhere above the x-axis, this is y is equal to 3. We haven't moved horizontally left or right, so this means we're going to keep it at x equals to 0. I'm going to label this. So we'll just label this at the bottom, just so we don't draw over ourselves. Now, you can see this is a positive truncus. There is no reflection in the x-axis. So we're going to have curves in the first and second quadrant. Something like this. And 2 curves approaching both asymptotes. So the line is going to start from somewhere near the asymptote and end towards the other one. Okay, are we done here? Kind of looks like it. It's pretty complete. But at the same time, why do we even state this down? Because remember, the examiners aren't looking for what the dilation is from the x-axis. They want to be able to see this visually. How can we tell the difference between this one and, let's say, suppose if this number up here was 1, or if it was 5, or if it was 10, 100. We need to be able to differentiate between all those different graphs with different dilation factors away from the x-axis. So what you can do here is what we call finding a second point. Since this dilation here can't be identified due to no intercepts being plotted, we find a point, 2 points here, to represent the dilation factor. That can be any 2 points. So sub in value of x, that works out pretty nicely here. And here, let's say we want an even number at the bottom here. Actually, you can even go with root 2 if you want, because if you get root 2 down here, you get 2 over 2. So we're going to have section for second point, or in this case we actually need 2 points because we need to be able to see how much graph is stretching. So for the second point here, we need, I'm going to say x is equal to root 2. Actually, the easy one would be 1, of course. Sorry. So 2 over 1 is just 2. 1, 2 plus 3, 5. Get x equals to root 2, as we said before. We get 2 over root 2, which gives you 1. 1 plus 3 is 4. So you get 2 coordinates here. I'm just going to plot these down real quick. So 1, 5. Somewhere to the right of 1 is root 2. And it's a little bit lower, so it's going to be a y coordinate of 4. And that's how you can show the dilation. But this one over here seems to be a lot of negatives. So we often want to see as little negatives as possible so we can sketch it out. But in this case over here, it may be important to use the lonely export as we used very briefly in the hyperbola video. So in this case, we need the coefficient of x to be positive 1, not negative 1. But you may also recognize that if you want to manipulate this a little bit, just construct a negative at the top. Doesn't matter where you put the negative, it's a fraction bottom or top, doesn't matter. Recognize that x minus 1 all squared is the same as 1 minus x all squared. So, and the idea is that you're going to be taking a factor of negative 1 out twice. If you take a factor of negative 1 out twice, you're going to end up with negative 1 squared. It's just equal to 1. So that's why these two are equivalent to each other. Of course, if you expand it, you'll also see the same 3 terms from expanding a perfect square. Minus 2. Let's state our transformations now. So we got dilation away from the x-axis of 3. Remember, we're looking at the magnitude, not the actual positive or negative value. Translation away from the x-axis seems to be 1 over here. Translation in the vertical direction, negative 2, going down here. And lastly, there's a reflection in the x-axis, judging from this one over here, negative 3. Okay, so let's see what it looks like on the graph. So I like to draw the asymptotes first, just to see if there are any intercepts that we need to be plotting out. Okay, so over here, translating 1 unit to the right, so this means our vertical intercept is now x equals to 1. Translating 2 units down, so the horizontal one goes from y equal to 0 to y is equal to 2. Sorry, y is equal to negative 2. And we're going to be reflecting this in the x-axis. So instead of having 2 curves up here, we have them down here in the bottom 2 quadrants this time. Okay, so it's going to look something like this. So it does look like it's not going to hit the x-axis, but it will hit the y-axis. So we need to figure out what the y-intercept is. Relatively simple. Subbing x equals to 0. Observing the expression up here, we're going to have negative 3 on 1, so negative 3 minus 2, which gives us y is equal to negative 5. So 0, negative 5 is our coordinate. I'm going to be drawing a curve which approaches both asymptotes. Both sides. Okay, and the reason why we don't really need to do a second point for dilation or anything like that is because this coordinate here already tells you the whole story. Now, if you're suppose that your a value gets to a higher value than 3. So suppose you have your dilation away from the x-axis is a much higher number. It's 10 now. What does this tell us? It's telling us that we're going to be stretching the graph vertically away from the x-axis. So a graph like this is going to have a y-intercept around here somewhere. And it's going to be a lot lower than our black curve. Similarly, if you want to be decreasing this value lower than 3, then it's going to be appearing even closer to the asymptotes. So just make a note of that this intercept already tells the whole story about dilation. Okay, so that's about it for truncuses.